Welcome to the another video of the electric drive. Here, let us consider a source connected with a isolation transformer. Then let us have a rectifier circuit connected with the thyristors so that we can fully control the output voltage. And this AC supply is given to the single phase rectifier, fully controlled, and in the output we are connected with the RLE load. RLE load is generally used to represent DC armature. Let us take the value of R, nearly 5 ohm. The L is, let us make it different values like 0 Henry or 0.01 Henry or 0.1 Henry. Practically this is not the case for the DC motor, armature of the DC motor. Just for the understanding, we are taking these three different values. And let us take the value of EB as 100 volts. So these are the load parameters. And we will see that what is the output voltage, output current I0, and what is the output voltage over here. So that is V0. And also we are interested for if we give a supply voltage here Vs, and we can write that Vs is equals to Vm sine omega t, and let us say the input RMS voltage is 220 volts 50 Hertz, where RMS value is 220. So we can write here Vm is 220 into root 2 sine omega t, and this 220 root 2 is nearly 311.126 sine omega t. And if I draw this input voltage over here, this peak value is representing the 311.126 volts, and here this is your input Vs, supply voltage, and the isolation transformer is of like equal turn ratios, not 1:1, like whatever the value of primary turn, the same. So N1 and N2 have the same number of turns. And here the DC back EMF is taken as 100. So we will, if I represent here at, if 311 is here, so this will be your EB. So EB and Vs, these two values are given, right? And how the output voltage will look like at different circumstances, that we will see. One more thing, the thyristors are named like T1, T2, and T3 and T4. So T1 and T2. So we can say that T1 and T2 will be fired at a single time together, and T3 and T4 will be fired at a single go. And if the way the current will flow is this way, right, and it will come down like this. So this is the one of the way. So here the current is going in like this, coming out, and in the load the current is always going downward. Another option is that the current is in case here we have a positive, polarity is changed, So the current will go in this way, and the current will come down through T4, and it will come down here if it is minus. So current is going in this way, but in the load we find that the current is usually going down only. So by T4 it is coming up and it is coming down like this. So this may be one of the pattern in which we can see the output voltage, the polarity of the change. So output voltage polarity is always from plus and minus will be like this. So we can find out what is the average voltage in the output and average current after that. So we have taken one results here for a particular parameter. Like we have taken this as a 5 ohm, and EV value is 100 volts, VM is 311. So this represents the 311, and EB is, this is the EB 100. So what we can see is that there is an intersection of this. This will be represented as, we can write that as this is as theta. So this is 0. This value is theta. So we can calculate the value of theta Vm sine theta is equal to EB. So from here we can say that theta is equal to sine inverse of EB by Vm. So in this way we can calculate, and we will find that if I have taken the value of EB is 100 and Vm is 311, so it will give the theta as 18.74 degree. So this theta value is 18.74 degree. So it is starting at 18.74 degrees. Obviously, this is the 180 minus 18.74, and this value is here. You have got pi. Similarly, here you have got 2 pi. That is of 0.02 seconds. You have got 2 pi here and pi here, and it is intersection point is, these two are the intersection point. What we find in the output voltage is 0 is here, so we are getting the output voltage directly 100. At theta it is started following the output voltage Vm. So this Vm is being followed here. Just zoomed up, this value is same 311. This is the same 311. So this is following the output here, and at 100 it keep on maintaining the 100. Again it follows like that. We get the output voltage, and the output current is from 0. It is starting at theta, same at theta value it is starting, and then it is ending at 180 degree minus of theta value. The L value is 0, so we don't have any inductive effect. Okay, and let us go for another options here. Let us add the value of L, 0.01 Henry. If we add the value of L 0.01 Henry, theta is remain same. We haven't changed the value of like EB and Vm. No, alpha is also 0 degree. Alpha is the firing angle. It is 0 degree. So when we change the value of the L, what changes is the phi. Phi is the value. What is the phi? Phi is, you can write tan inverse of omega L by R. That is the value of phi. So this phi value is around 32 we'll get. So our objective is, if the L value is changing, how does the output going to vary? So this is the 18.74 degrees. So at 18.74 degrees the output is supposed to follow, because the firing angle is alpha is 0 degree. So you can see that alpha is at alpha equals to 0 degree, the thyristor has been fired T1 and T2. So at this particular interval T1 and T2 is working. At this interval T3 and T4 is working. So since it is fired, it will not work, because you can see that EB is, obviously EB is greater than the VS right now. So till this line we'll get a output voltage as EB. Then the EB output voltage is going to follow the input voltage. This after this line, means after this theta value, then what happens, because of the inductive load, it is going downward, but it is not going below 0 degree, below 0 value. 0 is over here. This is the 0 line over here. This is a 0 line, so you can find that it is not crossing 0 line, it is at 0 line only. And the reason is the current is continuous. See, the current line is this, and what we can, this current is just continuous. So at steady state, what we find is the output voltage. This is the one cycle, like 0.02. After that, we are falling, that output voltage is just falling from like a full wave rectifier type. And since this is a continuous conduction mode, it comes to the continuous conduction mode because of the effect of inductance. Now let us increase the value of L to a very high value. What happen is, it's starting at the same place, theta, and it goes like this. It goes below also, like it's like 0 line. It is not going below 0 line. It is just like falling like full wave rectifier type. And here the output current is for, this is for T1 T2, and again T3 T4, again T1 T2. So you can find, if I want to only want for T1 T2, this is the current, then 0, then T1 T2 will have a current like this. So the moment T1 is fired, we are getting output like this, and the moment T3 is fired, we are getting a T3 output current. So the current is not starting from 0, rather it is starting after like just it is, current is there, and suddenly the current is started with some value of the current, and it continues, and suddenly from high value it will go down. And this is the difference we will observe. Let us come down to the again the baseline. L is equal to 0 Henry, and alpha is 0. Let us change the value of alpha. If we change the value of alpha here, let us say alpha is 10 degrees, theta is 18.74. We intensely take it 10 degrees less than the 18.74. What is the effect? At 18.74 only, it is following the output voltage. At 10 degree, it is not following the output voltage. It is following the output voltage at 18.7, and it's just like, it is again like this is dominating part. The current is starting from 0, and it is ending at 0. It is a discontinuous conduction. Let us change the value to alpha equals to 40 degree. Now this, it is 40 degrees greater than, right, from the theta value. So now in that case, even though it is 18.74 degree is that theta value, alpha is 40 degree, so it is falling from alpha, like this is a 0 line, right? So this is 0 line, and it is falling from here 40 degree, it is starting, and it is end, it should end over here. Then it is again the same 100 volt, then it is moving up and it is going down. Remember, the value of L is 0. That is the reason that it is not going below 100 now. It is remaining at 100, and it is falling like this, and the current is falling from here, and it is reaching over here. So this is what we observe at alpha equals to 40 degree. Now doing some changes, that let us say the practical, like L equals to 0.01 and theta is there, and alpha is equal to 40 degree. Now what we observe, that it is starting at 40 degree. Okay, fine. It is falling over here, starting at 40 degree, falling here up to here. Then it is going to 0, no doubt. From 0 it is still going down because of the inductive effect. So these are all the, because of inductive effect, we are getting the line from here to here. 0 line is this. So because of inductive effect, we are going up to here, and then it is coming at E equals to 100 volts. My firing angle is 40 degree. So at 40 degree only, it is going to follow the value of Vs. But below 40, it is just like E is the value. Below 40, EB is the output voltage. After 40 degree, we are getting the output voltage like this. And here again 0, and again some negative, and like this. So since the discontinuous conduction, we are getting the output current is starting at 40 degree only, and it is ending at this value is this is also called beta. beta is the extension angle. So here alpha and beta is the current duration is from alpha to beta. The beta value is after pi. So beta value is after the value of pi. So pi is here, this is beta somewhere, and this is alpha plus pi plus alpha. So pi plus alpha is over here. So like this we are getting the output pattern. So this is a little bit short video on the single phase rectifier fed to the RLE load. In the coming videos we will be having much more discussion on this.